Światosław is going to tell us about Semibounded cohomology.
Thank you. And thanks to Jarek Kędra for accompanying me with all this things. So that's for having something. Right now, there is definition. Non-homogeneous cochains on the group and derivative. And those functions, they lead to the well-known notion of group cohomology and things which lead to many applications in mathematics. And I would like to speak about one particular aspect. So after we did what we did, we learned that some other people were interested in the same thing, and for them, the story starts with group extensions. We take any group, we take a two-cocycle, and you produce another group, which is a set which has a product, but has this twisted composition. Okay. And some people also ask the question, when this group extension is the same as the product from a metric view, when the two groups, the trivial extension and the extension given by a cocycle C, they are quasi-isometric. And so some people understood that if this cocycle is bounded, then this is the case. I'm not sure how much time did it take to give if and only if answer, but that's the answer. It was first given by Klein and Lieb in some other language, but recently Frigeria and Sisto, they gave the answer in terms we like. So the answer is that if I can find a representative of my cocycle, because the extension does not depend on the cohomology class of C. If I change C by compounded, it's the same group. It's easy to write an isomorphism. So if I can choose this cocycle to be bounded in the following sense, if I fix the second variable, then I get the bound function, then this group is quasi-isometric to the trivial extension. So it doesn't take much to generalize this idea to subcomplex of non-homogeneous chains with the following problem. So after I fix everything except first P slopes, I would like to have a bound function. Yeah.
What kind of thing do you have on Z? I mean, is it the trivial reaction and easy?
So on the first slide, I use this dim color because most of the time I'm using trivial coefficients.
Okay.
So most of the time it's either Z or R. There will be one particular case quite soon with different coefficients. So this is basically the.
Does the theorem with web trivial extensions also hold for acoustic coefficients?
I don't know.
Okay.
I'm not sure.
Yeah.
Yeah. So we are interested in chains which are bounded after you fix every cell after the first P. So if P is large enough, you just consider bounded cocycles. If P is 0, you consider all the cocycles. It's not which morally interpolates between bounded and usual cohomology. So that's just the justification. for the name semibounded. Okay, p-bounded.
Question related to the previous one. So these extensions are always asymmetric, but can they say something about whether they are coarsely equivalent as coarse loops?
But coarse equivalence is just a metric property.
No.
No. So I don't know what is coarse.
Real.
Okay.
Okay, later.
So again, I'm not going to speak about to speak too much if these are non-trivial conditions, but that's chain complex. I have the group, and together with this group, I have comparison maps. Like
so this right here is no condition at all in low degrees, right? In degrees less than p.
yes.
Okay.
If degree is sorry, I said it wrong. If n is smaller than p,
Yeah.
then I just want it to be a bounded function. So if p is bigger than n, I just have bounded cohomologies. So I'm more interested. I will be interested in case of smallest possible p, so p equal to 1 person. Okay. So I have those comparison maps which go from p equals 0, which go with p equals infinity. I mean bigger than n. So that's the bounded cohomology, and decreasing p step by step, I will end at the usual cohomology. Okay, those are my comparison maps. And the thing which is not on the slide and won't be is the comment that the same proof which tells you that usual comparison map from bounded to usual cohomology is trivial for amenable groups here works as well. I will probably make use of this observation later. So the reformulation of Friederian system theorem is that this extension is quasi-symmetric to a product, even only if my class extension class is in the image of the comparison. Okay. So we are interested, as you may remember from the previous talk, in various metrics on groups. In my case, our metrics are not invariant, they are usual metrics, usual length functions on the group.
Just
Yeah. I need a usual triangle. And so. And usually people write this non-degeneracy property, which for me is not a property at all. I will need soon something real. Let's have it in green. And our observation is that if C is one bounded cocycle, then this function I defined below is a length function. So again, the only thing to prove is triangle inequality, which can be done easily by hand. But instead, I will use another observation we made. So we can treat our bounded cocycle as a map from smaller type of elements of G into functions of G. Just using the first one as a variable. But this map is an obvious map, but it's not a chain map. It is obvious it's not a chain map if you look at two differentials. One misses one term, so it cannot be a chain. Okay? But if you start to think what is the problem of this map is that the derivative is a constant. Okay? So instead of thinking of functions on the group, bounded functions on the group, I would think of bounded functions on the group modulo constant. That's a good module. There is a well-defined module. And it's it doesn't take much to prove that this map is actually an isomorphism. So starting with one bounded two cocycle, I'm getting one cocycle in values in this normed space. Okay? And if you know something about one cocycles, you know that they are basically the affine part of affine action. So you have representation, group acts here, there's a linear part, and you have one cocycle which gives you the translation part of the action. So starting with one bounded two cocycle, I get an affine isometric action on this space. And I can just pull back norm from the orbit. And that is exactly the norm I defined in the middle of the slide. Okay? So now, how do we use this norm? So that's the second part of the story. I'm interested in symplectic manifolds. That's the definition. If there are any questions. And so the basic property of this structure given by closed and non-degenerate two forms that I can, so non-degeneracy allows me to switch between vectors and one forms. And you see that vectors which preserve the symplectic structure are exactly one forms which are closed. Okay? And among closed one forms, there are exact one forms. So diffeomorphisms generated by exact one forms are called Hamiltonian, and this is the group we are interested in. We would like to understand something about this group. Okay, yeah, that's it. We can say something about particular classes, like manifolds. Those are those manifolds for which, if I go to the universal cover, my symplectic form again is exact, and it's a differential of a bounded section of potential bound. There are lots of them. You can start with surfaces homogeneous. Universal cover is hyperbolic space, and if you look at this upper model of hyperbolic space, then this lambda would be, for example, dx over y, which is constant length one fold. Okay, and if I speak about length, I mean that I take a metric pulled from the quotient. Okay, it does not depend on the metric on the manifolds, provided n is closed, which I should write down. And there are many examples of that. The first counterexample is a torus. So we start with a torus with a linear symplectic form. We go to the universal cover. The symplectic form is dx dy, and the only, the first pre-image, the first pre-derivative you think about is x dy. It blows, right? As x goes to the infinity. Yeah? It's not a poor choice. If you look at the isoperimetric inequality, if you look at the integral of your symplectic form over a disk, it grows quadratically, and the length of the boundary of the disk is linear. So lambda also has to drop. Okay, but still there are lots of interesting manifolds and groups, Hamiltonian groups. We can ask, we can learn. So for this, I needed a notion of undistorted elements. So Jarek was speaking at the end of his talk. So I would like an element to grow at least linearly, to call it undistorted. And that's everything I need for formulation of a theorem, first proved by Polterovich, and then we did some shortcuts in the proof. So theorem says that if I have this closed symplectically hyperbolic manifold, then on the Hamiltonian group of M, I have a metric such that every element is undistorted with respect to this game. Okay? So the importance of this theorem is that it prohibits lots of groups to be subgroups of Hamiltonian diffeomorphisms. So, for example, if your group is finally generated, then there is this word node, right? If we take a finite generated set, and you ask how many generators do you need to write your element with them. Okay, and this is the biggest norm, okay, in the description set. So there are tons of groups with distorted elements. Probably the easiest example to explain is 3x3 matrices. And if you look at this simple equation, Eij is a matrix which has one from diagonal, one at the entry Ij, and zeros everywhere else. Okay? So this equality tells you that if you would like to compute this translation length for an element E13, that it grows at most linearly in N, not quadratic. Okay? So this group cannot act with Hamiltonian, as by Hamiltonian diffeomorphisms. Also, the second group is not good. Okay, and what did we do in the proof? So we wrote this formula. We wrote this G to cocycle. It's completely trivial to check the cocycle identity. And it's the cocycle of the whole group of symplectic of diffeomorphism, this universal pattern, any exact symplectic manifold without H1. And we established some properties on subgroups. So first on trivial result, using a hard symplectic geometry, is that actually the group we are interested, the Hamiltonian diffeomorphism of the small manifold, they are subgroup of the Hamiltonian diffeomorphism of the big group of this group preserving symplectic form of data. Okay. So I have nothing to say about this theorem except that morally, what you need is, okay, you are trying to lift the action on a small manifold to the action on the current. And the problem is that, okay, you have a group which is connected, right? Because everything is generated by the flow. So you start to lift along the flow. And the thing you worry about is, okay, I will go along some loop. I will end up at the identity. Do I lift it to identity or some back transformation? Okay? And this could be checked by just tracing one point. So I have this loop of diffeomorphisms, and I evaluate it on a single point. I get a loop at the bottom, and the question is, does this loop in the universal cover open? Okay, so there is a evaluation map from group of Hamiltonian diffeomorphisms from pi1 of the group. I mean, there is a map from the group of Hamiltonian diffeomorphisms to a manifold. That's just evaluation map. And this map also gives you a map from pi1 of the group to the pi1 of the manifold. And basically, this result tells you that this map is free. Okay. So I forgot who is responsible for this theorem. It's in the book of McDuff and Solomon.
Maybe something stuff.
Yeah.
Nobody's responsible. Like it's responsibility.
Okay. And then our work is to show that this cocycle is bounded on this group. It's a calculation. Okay. It's also bounded on pi1 of our manifold, which is also interesting because, as you remember, I told you that I thought I will speak a little longer, so I removed this part from my slides, so I have to wave my hands a little bit. So you have this cocycle, which is in particular cocycle on a deck transformation. Deck transformations preserve the form. Okay, and there is a map from cohomology of the fundamental group to the cohomology of the manifold, given by the how do you call it, this classification, right? So it's standard to see that our cocycle maps to the same homology class as the symplectic form. Therefore, it's non-trivial. Okay, but therefore it's also non-trivial in usual homology of pi1 of our manifold. But on the other hand, it comes from one bounded. And as I told you, the comparison map would be 0 if fundamental group was amenable. Therefore, as a corollary, we get that the fundamental group of symplectic hyperbolic manifold is not amenable. Right? That's the second theorem. I should put it as an application of this bound. Okay. I thought that someone will question me why do I fix the wrong coordinate. But the point is that as long as coefficients are trivial, I have this symmetry. I can change the left and right sides. So if I was fixing the first variable on previous slides, I can also fix the second variable and get the same result. We just historical reason. Thank you. No, the funny part is I could have written anything.
All right, any questions?
Okay.
Okay, well, let's take this. You said.
No, there's a lot of questions.
It's the last session.
No.
Don't say anything. Say very specific. Is that important? I let you.